Ну, как-то людей немного. У нас нет еще 2 докладчиков, да.
Угу. Может, они к другой ссылке присоединились, к треку A, который...
Надеюсь, что нет.
Ну, вряд ли. Но первый докладчик все равно у нас есть, поэтому надо будет начинать вовремя, да и все. Докладчица.
Что-то я волнуюсь.
Да, тут очень волнительно. 5 человек сейчас.
Это еще волнительно.
Включая тебя.
Не по-английски.
Что?
Не по-английски говорите.
Ну еще же не началось, ладно.
We have to?
Вас уже
транслирует?
Да, трансляция уже идет.
Okay, we can start.
Yeah. So, hello everyone, my name is Alina Boyka and I am your moderator for today. And today we have 3 sections on game theory. And in the first section we have 4 presentations. And your chairs for today is Professor Елена Парилина and Ekaterina Gromova. And so during the presentation, all audience be muted, and after the end of the presentation, you can unmute yourself and ask your questions. All your presentations should be not more than 12 minutes and 3 minutes on questions. And also you can write your questions in chat and Zoom, and you can write in comments in YouTube. So I suppose that's all, and we can start.
Okay, hello everybody. Let me introduce myself again. I'm Ekaterina Gromova and I will be a chair of the first session in the track B. So now we start our presentations. Each speaker will have 15 minutes for the whole talk. So approximately 12 minutes for the talk and 3 minutes for questions. So please, the first speaker will be Yaroslavna Pankratova with a joint work with Leon Petrosyan on Nash equilibrium in repeated hierarchical games.
Okay, thank you. Good day, dear colleagues. As I said before, Professor Ekaterina Gromova, that I have today I will present my joint work with Leon Petrosyan on Nash equilibrium repeated hierarchical game. So at the beginning, please look at the picture. Here you can see some hierarchical system. There is M plus 2 players. This system has 3 levels. At the first level, we have a center A0, and this center can represent the interests of society. On the second level, we have several players, exactly M players, and they can represent regional interest, including the issues of environment protection, for example. And on the last level, we have the player C. C is manufacturing enterprises, for example. So how can we present the interaction between the players? We suppose the control of player C depends on controls of players on the previous level. And the set of controls of player BI depends on control chosen by player A0 at the first level. So at the first step, player A0 moves and selects some element U from the some set of strategies or controls where, and this element U restricts the possibility of players B1 and so on BM to make their chosen at the next step. At the second step, player BI chooses a function of the parameter UI. And this elements, this function U omega, selected by player BI on the second step specify restriction on the set of choices of player C as the third steps on the game. Denoted by C, the set C, which depends on the elements omega 1, omega m, and the element of these sets we designate by V, and under V we'll understand production programs. So in this game we will suppose that payoffs of all players depend only on the choice of V, so only on the production program. And we suppose that each payoffs for each player is non-negative, so more or equal 0. So before, it is clear that we can construct some game in normal form, but before we do it, let me introduce 3 conditions. This condition help us to construct interesting Nash equilibrium in the game, which we consider later. The first one, for any omega and for any O from this set of controls, there exists some element V0 from this set, such that all payoffs will be, for all players in the game, will be equal 0. This is the first condition. The second one, that for any U, there exists such element omega I U from the control set of players of the second level, that the set C will contain one element V0. This element from condition number 1. And in the last condition number 3, there exists such element U0 that the sets BI will contain only one element omega 0. So why we should consider such condition? This condition allows high-level players to paralyze the action of lower-level players completely. And from another side, the lowest level players can paralyze the action of high-level players. You see, so as in these cases, the player on the third level can choose this element, and all players, the strategy, and all players and all other levels will have 0. So now we can construct the game in-person game in normal form, as you see, where U is a set of the strategy of the first player, B bar 1, B bar M, this is set of strategy of the players from the second level, and C, this is set of strategies of the last player C. Here we define the payoff function the following way we defined it before, and so in these cases, we construct the game in normal form, and the solution in this game of normal form we will find as a Nash equilibrium. But the game which we construct before is the generalization of rhomboidal 4-person game considered in the paper Petrosyan-Zienkiewicz game theory, and for this game was proved the lemma, and we have such just generalization of this lemma, that the strategy profile is a Nash equilibrium in constructed game gamma, where V star we can find as a solution to parametric optimization problem, and we suppose that this maximum is achieved. Omega star, omega M star, we can find as a Nash equilibrium in some additional parametric game and person, where we construct the Nash equilibrium and the conditions that we know what is V star. And O star we can find as a solution to the optimization problem and the condition that we know V star and omega star. So this lemma, we proved this lemma, and we know that in such game exists Nash equilibrium. After that, we would like to consider a repeated game. So we consider infinitely repeated game G with a finite game gamma played on each stage. So in these cases, we can define the payoff of the player E1 the following way. This is just sum of payoffs of this player on each stage multiplied by the discount factor delta. Delta can be equal some value from the interval 0, 1. And the same way we can define the payoff of the players of the second level, and the same situation for the last level. Just this is some simplification, and we can rewrite this function following way. So it is clear that in such infinitely repeated game, we have many different Nash equilibrium. One of them, it may be just repetition, the Nash equilibrium that we considered before, repetition in each stage. But of course, we know that in such type of game, there are many Nash equilibriums in strategy. If we use this punishment strategy and the strategy these treats. So now we consider two possible types of such equilibrium. The first one, this is Nash equilibrium and punishment strategy. So how can we do it? We can consider some stage strategy profile and find some condition for which this strategy profile will generate and such this strategy profile will generate Nash equilibrium. How can we do it? It's very easy. It's clear that after getting on some stage L-1 the information about the choices of player C, the choices, this one, player C can, instead of the following the instruction made in by players from the higher level, choose another strategy. For example, such strategy which maximize his payoff in stage game, something like this. And so in these cases, he can get exactly on stage L some payoff which maximal value from just in the usual. But on the next stage, and always after in infinitely game, B1 and so on, BM can punish C by selecting VI0. This is value from condition 2. So in these cases, of course, after this one, the payoff of player C on each stage will be 0. So in such cases, of course, we can find such delta bar from this interval that the payoff in infinitely repeated game with deviation will be less for player C than payoff in infinitely game without deviation of player C. As you see, this is payoff which he can get in without deviation. This is payoff which player C can get this deviation. We can compile this value and we have the following results. So we can find such delta that these conditions, this inequality will be fulfilled. So of course, for any situation, we can find such delta, and considering strategy profile will be Nash equilibrium. But moreover, from this one, which formulate now theorem, but moreover, the deviation of player A0, B1, BM from 2 gives also the similar results, since BI can punish A0 if he deviates from some U tilde by choosing omega 0 from condition 2. And as a result, C will choose V0, and so in these cases, all players will get 0. So we have the following theorem. In infinitely repeated game gamma, there exists such delta bar from this interval that for all delta, the payoff on the arbitrary strategy profile this way can be achieved in some Nash equilibrium. Moreover, it's possible to modify this Nash equilibrium. For example, the players, all players follow arbitrary behavior for the first stage, and after that, all the rest of stage, they can use Nash equilibrium. In these cases, of course, we can find the delta, and such behavior will generate Nash equilibrium too. This is theorem about Nash equilibrium and punishment strategy. Here we can formulate the Nash equilibrium in treat strategy. For example, in each stage game, fix the vector function and define such strategy for player C. We start with the solution of our parametric optimization problem 1, which we considered before. Player C can declare in the beginning of the stage again that he will use this strategy. Then filling the treat B1, BM will be forced to use this vector. This is a vector which the player C wishes to get. in either case, they can get zero payoff because if the player C use this one, all players in the game will have zero. So we have the following theorem: the strategy profile such way where U star is the best reply of A0 against this one is an equilibrium in Gamba, and its repetition is an equilibrium in an infinitely repeated game. So after that, we can...
I'm sorry, you have to conclude because you have 2 minutes to finish.
Yes, the first one, we just construct cooperation form and consider 2 definitions. The first one, this is price of anarchy. You see this one. This is A, where V and bar is the maximal joint payoff in the game. And we have the, sorry for this one, yes. And in these cases, we have the price of anarchy equals infinity if we consider the worst-Nash equilibrium, because in these cases, we have 0. And another one, this is price of stability. We can calculate it using this ratio. And in these cases, a price of stability will be equal 1. So that's all. Maybe I just conclude some important things from this information. For this type of game, I mean, hierarchical game, individual behavior of the players can give infinitely worse results than cooperation. That's all. Thank you.
Thank you for your talk. Thank you very much.
Yes, I have.
1 or 2 very short questions, please, if any. I can ask the question. So you used this rhomboidal, how to pronounce it in English? Rhomboidal form of the hierarchy. Is it possible to apply the same approach to another
Yes,
form?
we did it. We did it for 2. Yes, we did it for 2-level hierarchical game. Just for if we have 1 or 2 without this one, we have the same result. Price of anarchy equals infinity 2. Okay, Ekaterina Viktorovna, something happens because I can hear you. All other person can hear, Professor.
No.
No?
I hear you. No.
She's frozen.
Yes, I see too. Okay.
Maybe
that's all question.
Right to her.
Yeah, thank you for your presentation.
Oh, thank you. Okay, if some question, you can just write me, ask me. Okay, that's all. I can stop the presentation. Yes. Can I stop?
Yes. So our next presentation is Ekaterina.
Okay.
Yes, I'm here now because I had a period of unstable connection, so I didn't hear the answer of Yaroslavna Pankratova. Sorry, so you will repeat me next time.
Yes, okay, next time. Okay.
So this is my turn. I'm sorry. So this is my presentation. This is a joint work with Anna Tur, who is also here now, I see, and also Polina Barsuk. Now she is a student of High School of Economics, and I believe she is not here now in our session. So I present a work which is devoted to the application of differential games to the problem of the pollution control. And especially it will be applied for the problem arises in one Russian region in Eastern Siberia. So as you of course know, it is clear that the pollution control problem is one of the major problem of the recent time. Especially this problem is very acute these days when we have ecological catastrophe in Kamchatka region, and but we tried. Our intention was to find not toy example as it's usually done in differential games, just not with some numerical numbers, but with concrete real data from Russian region, which will help us to understand what happened in this for three enterprises which produce aluminium and they are located in Krasnoyarsk, in Shelechov, Bratsk, and Irkutsk. So it is pointed on the map here, and we will demonstrate our results now. So the contribution of the paper which we submitted to the conference is twofold. First, we were able to find analytical solution of the theoretical pollution control problem. I mean, game theoretical pollution control problem in analytical form. So we were able to find the solution of the differential game of the pollution control for the case when we have a non-zero absorption rate, and we also constructed the cooperative and non-cooperative scenario of the game and obtained the solution in the form of the Shapley value and so on. So the second contribution of the paper is that we used real data which we found in the open access form, and this part is mainly had been done by my colleague Anna Tur. So I am very proud to work with her because she was very concentrated on the on this part of the research. So what is the game theoretical statement of the problem? We have n players. So this is a very classical formulation of the pollution control game. So we usually have n participants of the process, which we will name players, which are companies or countries, and we consider the problem which starts in some time instant t0, which is very often can be considered as 0, and the problem will be finished at that time instant t capital. So the strategic control, the strategic variable of the player here is its rate of emission. Why it's rate of emission? Because really these countries or companies, they produce something, and their production usually proportional to the emissions they do. So we will control not the production, but the emissions. But of course, we will think about the production of something. So here we will say about aluminium production very soon. So the strategic variable of the player is its rate of emission, so the velocity of the emission, how many emission we will use per unit of time. Then the state variable here is x, which is usually represents the stock of the pollution, pollution. So we have to know, of course, the initial stock of the pollution. So and we will denote it by x0. So here the problem will be considered in the open loop form, but of course the problem can be also considered in a closed loop form and so on. What had been done in our paper, I would like to distinguish with the previous results. So the first attempt to consider the problem of the pollution control in game theoretical form with real data had been done in our paper with Anna Tur, in which we considered three largest enterprises of the Irkutsk region of the Russian Federation. So in this paper, really another enterprises, another time period had been considered, and of course in this paper, which of course can be considered as a pioneer work in Russia in differential game of pollution control. So with real data, we used very complicated model. So the model was considered with random time horizon, with Weibull law for the random variable which corresponds to the end of the game, and so on. So, and we didn't take into account that there is an absorption coefficient in the model, which corresponds to the self-cleaning capacity of the nature. Then another paper, my paper was published in 2006. But here I considered only theoretical model, which is simple but similar story, but don't have absorption in the model, so some results had been obtained. And of course, now we will consider some model which had been used in other papers. This paper was mentioned before. This is the book Dockner, Jorgensen, and so on. So I will go to their model. So we consider the dynamics of the state variable of the stock of the pollution in the form 3, very simple form. So it's linear on control and linear on X on the right hand side. And we consider a linear quadratic case of the utility function here, and also we consider linear on X pollution removal in the model. And then we consider cooperative form of the game. It means that we can the players potentially can join together to find the optimal strategies which will help them to save our nature, as we will see a little bit later. So we were able to find, by using the Pontryagin maximum principle, optimal controls in the cooperative case scenario and optimal trajectory. So here, as you can see, our controls can leave the compact set from 0 to BI. That's why we found the condition, so-called regularity condition, when the control of the player always belongs to the time interval, or to the intervals, sorry, from 0 to BI. And if not, so otherwise we will consider more complicated form of the control in the form 7. Okay, the same had been done for the Nash equilibrium for non-cooperative case scenario, and also we found this time instant t in which the controls will reach the maximum level of the maximum permitted level BI, and we will consider this complicated form or more complicated form of the control. So if you will put it on the graph, you will see that for Nash equilibrium, which is line blue, and for red blue, we have these pictures for the optimal controls of players. And also there is a difference between Nash equilibrium and cooperative trajectory, which is not very well seen on the left-hand side, but we will zoom it, and we will see that Nash equilibrium will also give there more emissions in the nature than for the cooperative case scenario. So I will skip the next few slides, and we will approach to the final part of the presentation. So we take 3 aluminum plants at Krasnoyarsk, Bratsk, and Irkutsk. And we were able to estimate all parameters BI, also DI in our model. And we have this table of the parameters for 3 participants, for 3 players. And we substituted in the formulas which we obtained in analytical form. So what we can see from here, we can see that the difference between Nash equilibrium and cooperative trajectory always positive. So in Nash equilibrium, we will pollute more than in cooperative case scenario. And delta, this is a self-cleaning capacity, coefficients which correspond to the weather condition. So if the weather condition is bad, we will get less delta. If the weather condition is more good, we will get bigger delta. So for the bad weather, we will more big difference between Nash equilibrium and cooperative case scenario trajectory. And also I will finish my presentation now. So we will see that in the, I believe that this is the last table, we will consider the difference between Shapley value, this is the cooperative solution in cooperative form of the game, and Ki, this is which is the payoff in the non-cooperative case scenario. So this difference will be bigger for the bad weather, for the worst weather conditions here, and also the intention for cooperation will be also for this Krasnoyarsk aluminum smelter, because they paid more than another players. So DI, which is the payment for the pollution removal, was bigger for this company, and they are more motivated to cooperate. So these are some future directions. I will skip it now. Some references. So thank you for attention. We have 2 minutes for questions.
Yes, I have a question. May I ask? It's very simple. Did you use another concept solution for in cooperative game, not only Nash equilibrium? Oh, sorry, Shapley value. Did you use only Shapley value?
Not in this not in this paper, but we used Harshanit dividend, for example, and of course we try to consider core.
Okay, but what happens with core? Because could you say something? Or not for this paper?
In this paper we didn't.
No, okay, so thank you.
So any more questions? No?
How do you think, Ekaterina Viktorovna, that if you will apply the core as a concept solution in this example, it will be the same result?
What do you mean? That the players
I
will
mean,
be
the
motivated to cooperate?
Yes.
Yes, we did it with Polina Borsuk. We continued this investigation. Yeah, so it demonstrates that really we get the result which you said.
Thank you.
Thank you. Katerina, thank you for your presentation.
Thank you. Thank you very much. So the next speaker will be Li Yun. He is here now. Yes. The title of the talk, Dynamic Shapley Value for Two-Stage Cost-Sharing Game.
Okay. Hello, everyone. This is my title of report. This is outline of the report. And at the beginning of the report, I would like to explain 3 questions about the game model. What is this model? What happened to the model during the game? And how to modify the solution of the game? What is model? It is an n-player and 2-stage game. In each stage, a minimum cost spanning tree is played. Minimum cost spanning tree game is played. And the second stage, player may change the graph using strategy profile with transmission probability. This is as shown in the picture. There is a minimum cost spanning tree based on full graph in both the first stage and the second stage. The red and the green arrows in the upper right corner represent a different structure of the spanning tree in the first stage. Then different structure of the game, different structure of the graph in the second stage. will be the probability of them will decide by different structures in first imperial stage. And how to modify solution of the game? We use imputation distribution procedure and construct a dynamic Shapley value. But the dynamic Shapley value in this model may be time inconsistent. And here are several definitions. I can explain the definitions, important definitions of cost matrix. Each element of cost matrix is decided by players. For example, for the element of cost matrix CIG, CIG is equal to CGI is decided by the strategies XIG and XGI. Here, XIG, it means the player I play against player G. XGI, it means player G playing against player I. It means the cost of edge, IG, only decided by two players in the end, on the edge, player I and player G. For example, in this full graph, player 3 and player 4, the cost of edge 3, 4 is equal to the cost of edge 4, 3 is equal to the function FC. So the cost of edge 3, 4 is decided by strategy of player 3 and strategy of player 4. So if we consider all players simultaneously select strategies, we assume that they select a strategy profile X1, X2, X3, X4, X5. Then the cost matrix will simultaneously determined. This is the definition of minimum cost spanning tree. This method is calculate the minimum cost spanning tree, which is smallest, and the sum of minimum cost spanning tree is equal to all edges in this spanning tree. For example, TX, it means this spanning tree in the graph, and this graph is decided. This graph is decided by strategy X, and TX is a set of edges 0, 1, 1, 2, 1, 5, for example, and the sum of minimum cost tree is all edges, the cost of all edges. Now I'd like to describe the game. At first stage, all players simultaneously choose their behaviors. It is an dimensional strategy profile. And in second stage, the game proceeds to second stage with probability. This probability depends on various strategy profiles. The probability is decided by the vertical Z key in the game tree and all strategy profile on various stage. Here I cite here I define a matrix is called the alpha matrix. The alpha matrix of the stage game in vertex Z key is divided as follows. and I cite the definition of Hartmann product. Hartmann product is a classical definition on theory, and using the method of Hartmann product, I define the cost matrix of stage game in second stage. For example, in the vertical ZK is divided as follow. It means alpha matrix helps the stage game change the graph. For example, in this picture, in first stage, all players simultaneously select strategy profile X1. And then for each verticals in second stage, Z2, Z3, and Zm+1, there would be different probabilities to corresponding verticals. For example, from Z1 to Z2, the probability is PZ1, PZ2, PZ1, Z2, X1, and we have another example, like first as a second presentation page, I showed a picture with red arrows and green arrows. Red arrows and green arrows, they have different minimum cost penalty. So for them, different minimum cost penalty on first stage will decide different probability on second stage. Z2, Z3. Here is a definition of carry test function. In two-stage minimum cost penalty game, assume that total cost of players is sum of the cost players on both stages. This method is cited from Professor Panina 5 years ago, and we use the Bowman equations, got cooperated strategies, and the corresponding strategy profile X bar is called a cooperative strategy profile. In a similar way, we can define characteristic function for correlation S, and because it is in each stage there is a minimum cost penalty game, we assume that correlation S is the set of player 1 and player 2. Correlation N without S is player 3, 4, 5. So in the minimum cost penalty game, correlation S will aim to connect a graph between themselves with the lowest cost, but correlation N without S, they want to maximize the cost of correlation S. Here are definition of characteristic function in some game, and this is because we have defined the characteristic function for correlations in the game, and in some game we can get we can define the Shapley value as follow. And in the second stage, the game proceed to the stage game on vertical ZK. ZK are different verticals on second stage. So for different probability, there is a different maybe different Shapley value on second stage.
Sorry, in 2 minutes.
Where?
2 minutes.
2 minutes, okay, it's over. This is definition IDP, and use IDP, construct dynamic Shapley value. And this is dynamic Shapley value. And in this model, the constructed dynamic Shapley value is time inconsistent. This is an example, and we can calculate the result. Dynamic Shapley value is time inconsistent. Here are several important reference. Thank you.
Thank you for your talk. Thank you very much.
Thank you.
Any questions? It's rather strange to see time consistency with only 2 stages. So I believe it is possible to generalize the result at least to 3 stages, no?
Yes, 2 stages is simple, but in each stage there is a minimum cost spanning tree. It likes a stage game and very complexity, but because all players may select different strategies and construct a graph, but the graph maybe has the same spanning tree. So the game would be rather complex. I plan to research 3 stages on L stage in the future, but here are several simply result. Simply result.
Because usually when we have time consistency problem, the last payments on the last stage should coincide with terminal payoffs. So is it possible to have some parallel with this result here or not?
Sorry, I don't understand your question.
Okay, we we will discuss it a little bit later.
Okay, thank you.
No questions now? Okay, thank you again for your talk. Could you switch off the presentation to make it possible for the next speaker to share the screen?
Next speaker is
Yeah, I will introduce the next speaker. So the next speaker will be Anastasia Malakhova with a joint work with myself. The title of the presentation is Dynamic Programming Equations for the Game Theoretical Problem with Random Initial Time. Anastasia, please.
Good afternoon, dear colleagues. It's nice to see all of you here. And my name is Anastasia Malakhova. I'm a PhD student of St. Petersburg State University. The topic I'm going to present today is called Dynamic Programming Equations for differential games with random initial time. Okay, just give me a second. We are going to talk for a little about game formulation and how random initial time nature is set in the game, follow some main assumptions for the game, and talk for a while about pair functional and how it could be constructed in such formulation. And of course, the important question here is a subgame and how the subgame forms with assumption of random initial moment, and how the conditional probability appears in such case. After, we would follow the optimization problem for cooperative case and non-cooperative case as well, and the approximation for optimization will be Hamilton-Jacobi-Bellman equation, which will be shown in work. So the game we are going to consider is the game of n participants, and it starts at random moments. Some TS corresponds to some cumulative distribution function, and dynamics of the game is written by some ordinary differential equation system for the state variable.
Anastasia, we don't see slides. We just
Oh, okay.
see the title.
Yep. Just. I'm sorry. I don't know what. Okay. Is it works?
Okay, now
like...
it's okay. Yeah.
Yep. Switched. Okay. So the game Gamma with n participants, we random initial time corresponding to some like probability law and the dynamics of the game. Of course, we are going to follow some main assumptions for the dynamic, like visible solutions. So the dynamic equation and the right part of dynamic equation should be a convex differentiable function. The state variable should belong to some open subset of finite dimensional, and the state variable takes constant initial value, constant finite initial value before the game starts and till the moment the game starts. And the controls we're going to consider are the closed loop strategies. And of course, there are some assumptions for the controls values. So the controls are taken out of the set of some admissible controls, and these invisible controls are consist of all measurable function of the interval, and they are taking values of some admissible control set value, which is convex compact, with all we need for the optimization to be done. So the optimization problem for the cooperative, for a non-cooperative case of the game for where player I is set as a maximization of integral payoff under assumption which H on the slide is where continuous function represents instantaneous payoff of the player. So here should be the index I. And here you could see that the random the moment of the start of the game is a random variable. So this wave function should be written in the under this presumption of randomness. So as the moment of start of the game corresponds to continuous distribution under our assumption, we could write the payoff functional as the mathematical expectation for the game according to cumulative distribution function to be which were considered. So payoff functional will take form of like integrals, like it's written on the slide. And the following results allow, like, there is a theorem that the payoff function for such a game could be simplified to the form written on the slide. It could be done through just assumption of that cumulative distribution function is continuous and that the intervals are finite. So through partly integration. And the point which is interesting for us here to consider Hamilton-Jacobi-Bellman equation is the subgame. And assume that we are going to consider some subinterval of our initial interval. The game, presume that the game starts at the moment theta. So the payoff in the subgame would be again a mathematical expectation, but the cumulative distribution function will take another form as its subgame. So we should take it in mind and like look for the payoff functional in the form of new probability space. And here we could follow the conditional probability, how the conditional kind of conditional probability cumulative distribution function, the CDF for new subgame, could be obtained. Let's look on the interval of the game, like from T0 to TF, right? to TF, and there is some moment theta where the game, where the sum game starts. So we could look into sub-intervals. For this case, like the interval from T0 to theta is the interval the game did start before theta, like put the events according to this interval. But for the interval from theta to TF, it's the event that game did not start before theta. And for the interval T0 to T is the event that the game did start before theta. So these two events are complementing to each other. And if we if we denote as event A is the event on this interval, event B is the event on this interval, and event C is the event on this interval from T0 to T, we could use the law of total probability to define the probability of event C as the sum of these two expressions here, like the event of the probabilities through the event A and probabilities through the event C. Also, we could notice that we could write probabilities for all three events separately as the probabilities for event C under conditions of event A, and finally obtain the conditional probability for the case that for our subgame cumulative distribution function will follow the expression 6 written on the slide. So, okay, I'm sorry. Yep. So we're going to use this expression in our mathematical expectation to integrate as follows, and to use the same technique as was used in the theorem mentioned above, to simplify from multiple integration to just like integral expression. And this could be done by integrating by parts. I will not stop here on mathematics, it's just like algebra. And finally, we could obtain here that simplified payoff function in the subgame would take this form. Here, I is just a notation from T, like basically I depends on like a set of variables mentioned before. And afterwards, we follow the maximization problem, the principle of optimality as a dynamic programming. I would also not stop on here, but I would show the approach how the Hamilton-Jacobi-Bellman was obtained. As we obtained before f of theta as a conditional probability, we could also write as well the expressions for the game starts at the moment theta plus some delta and the density function for it. And after, suppose that we introduce the value function for the player I as just like the payoff or maximization of payoff. And we could write again like the value function for the moment theta plus delta. It will take the form as written on the slide. And here are some like algebra coming as well. For our value function, we could substitute value function with first integral on two intervals. For the second interval, we could use the density function here to rewrite it for another density function for theta plus delta, and afterwards to obtain the expression for the value function from another moment of time. Afterwards, dividing by delta and taking into account the expression is written here, and aiming delta to 0, we could obtain the expression of maximization depending on the value function and on the partial differentiating for that value function. And finally, this is how the Hamilton-Jacobi-Bellman equation is gained with the value function defined on the slide as a maximization of the payoff. on the whole interval. So for the further development in this work, the games with several players would be considered. Each of all has its own random variable at the moment of entering of the game, and so the game formulation would be like complexified a little bit. So we will see that this is like kind of a little bit more interesting. And here are some references which were used during the work. So I'm sorry for being in a rush, just we are tough in time today. So thank you for your attention. If you have any questions, please ask. You're free to ask, I'm free to answer.
Thank you very much, Anastasia. So we will thank you. So we have 2 minutes, a little bit more for questions.
Can I ask?
Yes.
Anastasia, could you please give some examples of applying this model?
Like examples of process with random initial time?
Yes.
Okay, I think that there are plenty of it. Just like give me a second to think about the business, the trading, then the condition. Okay, for trading, you have to wait for an initial moment to be suitable, or for a counterparty to be involved in the process. So it's a randomness here. And this is the random point from which the process starts.
Okay, thank you. And
When we are waiting for some decision of the government, for example, so we have this decision and then we start the resource exploitation or something like this.
okay, thank you. Did you consider?
I do believe there are a lot of applications. No, it wasn't done yet, but I do not just do believe, but do know that there are a lot of applications to the theory, as it's like the simple assumption of randomness in initial of a process. So
okay. Thank you.
It could be applied. And yes, for further development, it would be nice to apply it to a real example, to develop it for some pictures and something we could touch. Thank you.
So other questions? No. So now let us thank the speaker again, and thanks to all participants of the session.
I'm sorry, we have one question in YouTube comments. Thank you for your presentation. Can you say how this Hamilton-Jacobi-Bellman equation is different from this equation for random horizon problem?
Okay, I don't like remember it by heart, but it's different in sense of probability structure, and I really like. I mean, I remember that I like compared this stuff between each other, but I believe that this is like the integration here is different because it's the different like part of the integral. To be used as the random moment of a start, so what is here?
No. The Hamilton-Jacobi-Bellman equation for the problem with random time horizons differs a lot from this equation, because when we consider problem with random time horizon, it can be considered as a problem with the discounting. With discounting of the payoff of the subintegral function. So, so it's very close for the problem with random time horizon. This equation will be very close to the well-known Hamilton-Jacobi-Bellman equation for the discounting, for the problem with discounting. But here is not discounting by itself, so it's a rather strange discounting, because we discount not discount, but we consider random initial time. So we this very strange integral part appears in the equation. So here we have integral, how to say, integral differential, ну, в общем, интегродифференциальное уравнение, equation here, and it was not before.
Thank you, Katerina.
So I believe that we have to stop now, if or maybe other comments in YouTube. No,
No.
no. Okay.
Thank
Let us
you.
thank again to all participants. We will continue in about 15 or 10 minutes, but it will be another chair. Elena Parilina will join to
But
us.
we will use the same link for the next.
Yes. You can stay here and
Okay.
watch some beautiful slides.
Okay. Anastasia, please, can
Yeah.
you? Okay. Bye-bye.
Bye-bye.
Thank you.
Павел, Александр, здравствуйте.
Здравствуйте, Ирина Михайловна. Я не
О,
Павел.
привет, Ярослав. Привет. Так, сейчас я включу. Как ты?
Чё?
Здрасте.
Первый доклад сделала, сейчас второй.
А, сейчас второй еще будет, да? Так, это вот все, что у нас, вот участники, это все, кто вот здесь висят, и все, больше никого нет.
А надо проверить, у нас кто делает доклад? Вот Павел Лебедев, наверное, делает доклад, да?
Угу.
И кто-то еще? Николай Никандрович, наверное?
Нет. У нас будет делать доклад Алена Евгеньевна Мочтакова.
А, ваша
Маштакова. Угу. Так, Павел, есть. Ярославна, вы делаете первый доклад, да?
Да.
Так, и последний доклад Надежда?
Надежда, да.
Ага, все, она присоединится к нам, да?
Ну, должна была с утра. Обещала.
С утра уже... с утра обещала, хорошо.
Какая красивая заставка у нас.
Очень.
Почему у нас здесь фонит? Так?
О, еще красивее.
Так. У нас очень жесткие временные ограничения.
Не успеть за 10 минут галопом по Европам получилось у меня. Сейчас еще хуже, сейчас еще больше информации.
Мгм.
Надежда с нами.
Я не вижу
Есть.
Надежду.
Надя здесь.
Да, меня слышно?
Да, да, все хорошо.
Прекрасно, спасибо. Так.
We have 4 minutes to start.
4 minutes, yes. We should be very, very fast, all of us.
Yes, I will try. Just look at this place, and this place. It's a previous section.
Maybe we need to have only 5 slides to be in time.
Yes, and you have 3 minutes in each one.
Yes.
Alina, now our section has a translation
Yes, yes, yes.
in YouTube, yes?
Yes. Because I first I got YouTube and I see after several minutes, when not several seconds, my voice is.
Yes, I see.
We can stop this translation, actually.
No, it's just.
But you talk in English, it's very good.
Yes, we'll try. This is the reason why I ask you about the translation.
But there is online translation into Russian?
Yes, in YouTube.
Yes.
Yes?
Yes.
So in YouTube I can change the language, Russian language?
No, only English.
Ah, okay, only English. Okay. So if we are in Russian, it is stopped translation?
No.
No,
actually not stop. Just for tomorrow, you talk in English. It's good, but other participants not
understand something.
They speak in Russian all the time.
We also, moreover, we have chatting in English. So it is a very high level of.
Very good.
Thank you.
Oh, Denis Vячеславович, how are you?
We can't hear you.
I can. We can.
I cannot.
Just use the room.
Fine, thanks. How about
Okay,
you?
great. We are fine.
Okay.
Happy to see you.
Аналогично.
Все, that's all.
Enough.
Yes. Enough happy.
Oh, Katya.
Hello, everyone.
Hello.
Hello. So, I think we need to be ready. Yes?
Yes.
1 minute. Yes, 1 minute. We wait for 1 minute. But we have no time for presentation of the speaker. We should be very, very fast.
Okay.
Yes. I will present you. No worries. So we start. Yes, we start our session. It is part 2 of session game theory, conflict system control. And the first speaker is Yaroslavna Pankratova. This is a joint work with Denis Kozyutin and Roman Svetlov. And please try to be in time. I will, and do not, I will tell you 2 minutes before the end, yes, to have 2 minutes for questions, please.
Okay.
Yes.
Okay, good day again. I'm very happy to see you here. So this is the second speech for today for me. I will present our joint work with Denis Kozyutin and Roman Svetlov, minimal current payment algorithm, sustainable cooperation, sorry for this one, for sustainable cooperation in multi-criteria game. So here, before I will start to speak exactly about our result, I would like to show you some related paper which help us to get the result which we have. The first one, this is Leon Petrosyan. Here you can see this one. This is about time consistency, and another paper will concern the sum game in extensive form. And this is our paper before we start this. This result is now in some maybe follows paper. So the first one, in this slide, we have some information, usual designation for multi-stage multi-criteria game. This is set of the players. K is a finite game 3. P is a set of positions in the game. So PI, this is set of player i's decision nodes. Pn plus 1, this is set of terminal position. So we can construct the path or trajectory in the game theory. So if you have multi-criteria game, of course, the payoff function, the payoff of the players is a vector payoff of player I, and each component of this player is positive, and we suppose that this payoff are transferable within the criteria. So in these cases, we consider this game in class of pure strategies, and each strategy profile can generate the trajectory such way. And using this formula, we can define the payoff, the vector payoff function in such game. As you know, each indeterminate nodes can construct this, can generate two object subgame gamma xt and a factor game in this case. So such decomposition of original multi-stage game gamma x0 generate the composition of the player strategy. So we have two types of set of player strategies. Yes, in these cases, so we can define the strategy profile and the strategy profile for subgame, and we have the same formula to define the vector payoff function for subgames. And this we have a rule how can we compare the vector payoffs, and the main equation, the last vector inequality applies that the vector B is Pareto dominated by A. And in these cases, we will consider the Pareto optimal efficient strategy. As you know that it's proved that this set is not empty, but may contain multiply strategy profile. As you hear today, the plenary speaker, this is just 1,000 paper. How can we choose unique? Leon Petrosyan said about this one. How to choose unique Pareto efficient strategy profile. So in our cases, we suppose some of this one. I mean, how can we choose the unique Pareto efficient strategy profile? We use minimal sum of relative deviation rule. This rule will introduce in this paper. And what we do, we consider the sum of all players' payoffs with respect to criterion K and find the maximum for all criteria. You see, so we have a vector, and this vector can be considered as the ideal payoff vector for grand coalition N. And after that, according to the this rule, I mean minimal sum of relative deviations rule, the player have to choose a Pareto efficient strategy profile U bar that minimize the sum of relative deviation with respect to criterion from the vector H0. You see this one. So in this case, this rule help us to choose the strategy profile, Pareto efficient strategy profile U bar. So after that, we have two cases. In one cases, this strategy profile may correspond only one path. So in this case, there are no problem. But if otherwise, for example, we have several paths which can be getting using the strategy Pareto optimal strategy profile. So we just use such way that have the minimal numbers, something like this. So after they choosing the strategy profile and according path to the strategy profile, we will say that this is a cooperative trajectory, cooperative path, and the strategy U bar we will call the cooperative strategy profile. So we will use the same approach in each subgame to find the strategy Pareto optimal Pareto optimal strategy profile in each subgame and in each subgame. So and the same situation if we have several paths. We will choose exactly the path of this number one. Very important remark, the Pareto efficient cooperative path W bar based on this rule, which we considered before, was proved to satisfy the time consistency property. It means any part of this path of this cooperative path omega in the subgame gamma x bar remains the cooperative part of this subgame. This information you can find in this paper. So continue. After that, of course, if we find this strategy profile and path which correspond to strategy profile. We would like to construct the game in characteristic form, the cooperative game in characteristic form. Of course, there are several methods how can we construct the cooperative game, but in this cases we use exactly alpha characteristic function. This is classical approach. So as a solution, we will use some single valid cooperative solution. In this case, we use exactly Shapley value. We will do in the same way in all sub games. And after that, we would like to construct some imputation distribution procedure and investigate its properties. So imputation distribution procedure-based approach implies that the players manage the current payments stream to inform the cooperative agreement. So let beta I, this value corresponds to each actual current payments which player I receives at the position X tau bar with respect to criterion K instead of this value according to the ADP beta. Now we consider some useful properties for such imputation distribution procedure. Just some very important, in particular, two novel properties an acceptable payment schedule for the multi-stage game should satisfy, which take into account the sequence of the player's action along the optimal cooperative trajectory. Was suggested here. So the first one, this is assumption rim, rewards immediately after the move. What means is very interesting assumption. It means, the formula you have here, it means the only player who can get positive current payments at this point is the player I, which moves at the previous position X bar T. Moreover, we have additional things. If the position X is the last player I's position along the cooperative trajectory, this player should get the rest of your optimal payoff right after her last move. So these properties were formalized, the so-called this one, reward immediately after the move. This is the first property. So we have the following definition. The first one, this is the imputation distribution procedure meets the efficiency condition if the following following equation is fulfilled. Equation 7 means that the sum of player I's actual recurrent payments along the optimal cooperative path equals to the total amount to be obtained by the player I encoding the cooperative solution. If equation 7 holds, then the payment schedule beta can be reasonably interpreted as a rule for the step-by-step allocation of the player's I's optimal payoff. This is the first one. Another definition, as you see, this is we say the IDP meets the time consistency inequality if this inequality is fulfilled. You see, the vector inequality 8 means that each player has an incentive to continue cooperation at every sub-game along the cooperative path. Another property, strong irrational behavior proof. Another name for this one, Young conditions. If for every player I, we have the following equation is fulfilled, we will say that IDP satisfies the strong irrational behavior proof conditions. These conditions holds, then every player has an incentive to cooperative even if she anticipates that the cooperative agreement can be violated at the intermediate position X bar T because of the irrational behavior of other players. This is additional definition, which initial properties which we need for
Sorry,
our
2 minutes.
Yes, so this is non-negativity constraint. We see this is each one is more than 0. So this is our procedure that give us the minimal current payments algorithm. We can use this algorithm and we have the proposition. For every multi-criteria, multi-stage game, there exists such MCP imputation distribution procedure that satisfies rim assumption, efficiency, TC inequality, Young conditions, and the non-negativity constraint. Last remark, the IDP beta constructed above implies the minimal current payments to the players among all the payment schedule meeting rim assumption and condition 7, 8, 9, and non-negativity constraint. That's all. This is just some information about how it can be compiled to possible way to use imputation distribution. Thank you. That's all.
Have you any questions, please? I have one question. As I understand, so you postponed the payoffs, yes, the payments to the players until the player moves. So he moves or she moves. After that, we pay for him or not?
Yes, only for such players. Yes.
So we do not give any money. So we save everything until the player moves. Yes, and all this works when you have positive, non-negative payments.
Yes, function. Exactly. And we give the minimal value, positive minimal value, and so we just I don't know, support the cooperation. People would like to be in cooperation to get the payoffs.
And you cannot like mix the payments within criteria. So if it is criteria 1, you cannot redistribute the money from criteria 1 to criteria 2.
We didn't, but maybe we didn't.
So you don't. So you have like different payment schedules. Okay. So now I'm done. Yeah. Do you have 1 minute for questions? If no, we can. Thank you for your presentation.
Thank you very much.
Thank you.
Yes. And the next speaker is Alena Mashtakova. This is a joint work with Nikolai Petrov. Please share your screen. This is a mini. I will not pronounce. The speaker will pronounce the work. Yes, please.
Can you please full screen?
Control L. Maybe it doesn't work. So it is like vid, and it should be somewhere here. Oh yes, great.
Good afternoon. My name is Alena Mashtakova. I'd like to present to you a report, Pursuit of Rigidly Coordinated Evaders in a Linear Problem with Fractional Derivatives, Simple Metrics, and Phrase Restrictions, co-authored with Nikolai Nikandrovich Petrov. First, consider the definition. Let f be an absolutely continuous function. The number alpha is in the range from 0 to 1. A function of the form 1 is the computer derivative of order alpha of the function f. In the space Rk, for k greater than or equal to 2, we consider a differential game of n plus m persons and pursuers p1 and so on pn and m evaders e1 and so on em. The player controls and their starting positions are set. In addition, it is assumed that the evaders don't leave the omega set. Let's introduce new variables z, I, j. We get the system too. Definition. A capture occurs in the game if there exists a moment t greater than 0 such that for any admissible control of evaders ej, there are admissible controls of pursuers pi, time tau and the numbers L and S, such that ZLS of tau is equal to 0. We denote the notation for the interior and convex hull over the set X. Theorem 1. Let n greater than or equal to k, a less than 0, and condition 3 be satisfied. Then a capture occurs in the game. Theorem 2. Let a equal to 0, n greater than or equal to k, and condition 3 be satisfied. Then a capture occurs in the game. Additionally, the following problem was considered. A definition: let f and the first derivative of f be an absolutely continuous functions. The number alpha is in range from 1 to 2. A function of the form 4 is the computed derivative of the order alpha of the function f. In the space Rk, for k greater than or equal to, we consider a differential game of n plus m persons and pursuers P1 and so on Pn, and m evaders E1 on M. The player controls and their starting positions are set. Alpha is selected from the range from 1 to 2. Theorem 3. Let a be less than or equal to 0. The number alpha is in the range from 1 to 2. Omega is the space Rk, and inequality 5 be satisfied. Then a capture occurs in the game. This slide illustrates the implementation of Theorem 3. So this concludes my report. Thank you for your attention.
Thank you. Do you have any questions, dear participants? I have. Can I ask you some questions? So you have evaders, yes, and the evaders have the same control V, yes? Or pursuers have the same control V or not? If you show us, so V is the same for any J. So in the right part?
Yeah.
Yes.
Control V is equal for any evaders, but any pure have control UI.
But how can it can be explained? So it means that we control all the players with one control. So they are like a center who controls everyone here.
Yeah, exactly. We have one center, and we choose the control of this center. So all evaders move in the same.
And what is the difference between, so you consider two intervals for alpha, from 0 to 1 and from 1 to 2. Is it significant for gamma? You show this Kapita derivative of order alpha, yes? So is it significant that you have these intervals, so from 0 to 1 and from 1 to 2?
Do you mean why we choose this?
Yes. Why only these intervals? Why not? Because alpha is greater than 0, so it may be any number, but you consider only two intervals. It is interesting why two of them.
Firstly, we tried to solve problem for any number alpha, but this problem was such difficult, so we choose only several intervals.
So, okay, but anyway, you may consider alpha which is greater than 2 as well, or not?
We consider, but nowadays we don't have any results.
Ah, okay, okay. Do you have any questions? Hello to our new participants. Yeah. So if we have no questions, so we can wait for until 7 minutes. Yes.
7 minutes.
Yes, and we can discuss everything.
Yes, we can discuss. We have very, very actual problems in game theory, so we can discuss them. Okay. We have participants from Canada. George, hello.
Yes, we see George, hello.
We are happy
We
to
can't
see you
hear
here. Yes,
your microphone does not work.
Maybe use, yes.
Hello, hi everyone.
Hello. Yeah, good
to see you all.
Yeah.
So we have a break of 5-7 minutes.
Yes, you can announce something from, from Canada.
Yes, we are running a series of seminars on dynamic games and applications every Thursdays from 11 to 12 Montreal time. So it's
from 6, yes, in Moscow.
6 p.m. in Moscow. So we have already some speakers. Tomorrow we have Lu who will be talking about a marketing problem and things like that. Anyway, you can find the information at Gerard's webpage, and maybe Elena can forward.
Yes, yes. The problem, George, that we have a seminar of Leon. So Leon announced the seminar at 5 o'clock. Yes,
okay,
so every Thursday at 5 o'clock we have a regular seminar starting from the next week.
Okay.
So if we finish at 6, sometimes it lasts 2 hours, sometimes 1 hour.
Wow,
so it depends.
You have a lot of things to discuss.
A lot, yes. So we will try to. We have a deadline, 1 hour, and go to your seminar. So.
If you can, it's otherwise maybe we can see if we can change the time.
But you announced the time on this website.
It has been announced, yes.
Maybe we can change a bit the time. So for us, it's easier because we haven't announced for now. So it is like an agreement before.
Okay.
So we will have 2 talks in this session. Then we have a break for 15 minutes, and then again 3 talks. Every talk 10 minutes, and it is like in a rush. So we are running.
Okay. Good.
A very fast presentation of the results.
So this is a control conference? Or?
Yes, this is the control conference devoted to the chief of our department. He started our department many years ago for control. He was a scientist in control theory, Zubov. And he was the dean of the faculty, the first dean. And after that, Leon changed.
For 50 years.
Not 50.
Almost. Okay, so we'll start in a couple of minutes. I'll be back.
Yeah. Yes, thank you.
So I suppose we need to get 3 minutes. Wait. We should wait.
Yes.
Nobody
it will be
talk.
We want to talk. Who is talking? Alina, we will talk with you. Yes.
Okay.
So you are specializing in which area?
In control theory.
Your supervisor is Nikolai Smirnov.
Yeah.
Yes. Okay. So you also start your research or no?
Yes. Actually, I will present my presentation on Friday.
On Friday. Okay.
Yeah. Also, I chair.
Interesting. You're a chair and you're presenting. Okay. But which part of control theory?
It's social economics models. But in control theory, it's non-linear optimal control problems.
Non-linear. And you solve it with numerical methods or not?
Yes, with numerical methods.
So you will be interested in seminar of George.
Sure.
Yes.
I am listening.
Yes. It will be interesting because if you are interested in social problems and control theory, I think it will be interesting for you.
Sure, I am here.
Thank you for information.
I will send you the link after this.
Okay.
And we have 1 minute for waiting.
Actually, I suppose we can start. 1 minute, 6 minutes.
We can start sharing the screen, and I will present because it is a long title, and I need to be careful. To present. So, Pavel, are you ready?
Yes, I am ready.
Oh yes, please share your screen if you can, and I will present. This is the talk of Alexander Uspensky and Pavel Lebedev. They presented Krasovsky Institute from Yekaterinburg.
Yes.
So they are our friends from this institute, and we have a strong connection with the institute. And the talk will be differential and algebraic relations in singular sets construction for one class of time optimal control problems.
Yes, it is.
Yes, please
now,
share. Yes, we are waiting.
Do you see our presentation?
No.
Wait a minute, please. Wait a minute. Yes. Now, wait a minute, please. I try to show my screen.
Yes. It's starting. Okay.
Well, let's start our talk. Also, we are from the Institute of Mathematics and Mechanics named after academic Krasovsky, and our talk is about differential and algebraical relations in singular set construction for one class of time optimal control problems. We consider the Dirichlet boundary value problem for the Hamilton-Jacobi equation, the minimax solution of which coincides with the optimal result function for one class of time optimal control problems. The approach to constructing a solution to a boundary value problem applied in this article is based on identifying the conditions for the appearance of singularity of a solution depending on the geometry of the boundary sets and the differential properties of its boundary. The problem of construction to a minimax solution of the plane Dirichlet problem for one class of Hamilton-Jacobi equation is investigated. So the equation 1 is the Hamilton-Jacobi equation, which describe the simple motions just from the circle with radius is equal to 1 and its center is in the beginning of coordinates, and the equation 2 is the boundary condition on the curve gamma, which is the border of the closed set on the planar. And here norm of the vector nu is not larger than 1. And this problem is closely connected with the time optimal problem for the system with a simple dynamic, which is described by the equation 3. The derivative of the coordinate x is equal to nu 1, and the derivative of coordinate y is equal to nu 2, and the norm of the vector nu is not larger than 1. So the connection between two problems is described, for example, by Andrei Izmailovich-Subbotin in his book about generalized solution of the first order PDE. And let B the function ρ dependent of two coordinates x and y and the set M is a Euclidean distance from the point on the planar with coordinates x and y to the closed set M. So this function is equal to 0 when the point is located on the curve gamma, which is equal to the border of the set M. And the theorem 1 is proved by the authors that function u from x and y, which is equal to ρ from the point to the set M distance, is the minimax solution to the problem 1 and 2. And we have a remark that this function is super differentiable at all points on the planar except the set M, but of course it is not smooth, and these not smooth singularities are described, for example, by Vladimir Fedorovich Demyanov and Rubinov in his book Foundation of Non-Smooth Analysis as Quasi-Differential Calculations. So we describe Dirichlet problem for the acanal equation 4 with the boundary condition 5, which is also closely connected to the Hamilton-Jacobi equations, but it describes the wave propagation of light in the planar set or in three-dimensional space. And the fundamental solution of the problem for equation 4 and condition 5 is described, for example, by Stanislav Nikolaevich Krushkov in his article General Solutions of the Hamilton-Jacobi Equations. It is equal to minus distance function from the point x, y to the set M. But the maps levels of the solution of problem 1 and 2 concedes. So it's an illustrative example of the wave fronts propagation and their singularities for such set, which is surrounded by the elliptic curve. And you may see the wave fronts. This around phi, and L it's singularities, and gamma is the curve of the set M. And then you may see on the right part of the illustrative example the optimal result function. So you may see that it is non-smooth on the singular set. And here the problem of defining the points of cell intersections or follow tails of equidistant lines are very important for the singularities. Then we introduce the bisector of a set. Let M be a closed set on the planar, and we denote the P from B is a set of points projections nearest in the Euclidean metric from the point B to the set M. And we denote that all points for which the set P from B consists of 2 or more of elements as the bisector L from M of the closed set M. So you may see the bisector of the parabola, and you may see the bisector of the B parabola. You may see that in the first case the bisector is quite simple, it's just a ray, and in the second case the bisector is more complicated. It has 3 branches and the point of bifurcation. So we introduced gamma, a continuous map of numerical interval big T, so that it describes the curve gamma as a function of 2 variables, x and y, like functions gamma 1 and gamma 2 from the parameter t, and let points t1 and t2 be from this set t, and we draw tangent lines in that 2 points, and a point x0 y0, which is the limit of the points x with the star and y with the star, is called a pseudo-vertex of a curve gamma, where x with the star and y with the star is the one parametrated subset of the solutions of such system 6, which describe the intersection of tangents such that its point of intersections is strictly on the level distance both from point gamma 1 and from point gamma 2. And here T2 from T1 is a local diffeomorphism, which is given by this condition 7, which describes these geometric relations. Geometric relations A1, A2, and A3. And the left one derivative lambda in point T0, which gives us a pseudo-vertex of the curve, is called the left pseudo-vertex matrix marker of this pseudo-vertex on the curve gamma. So we may see an example of diffeomorphism diagram and the pseudo-vertex of the curve gamma, which is described by a scalar function plot. And by a branch L from the point x0, y0 of the bisector of a curve gamma, where x0, y0 is a pseudo-vertex of gamma, we mean the set of points x, y on the plane that satisfies such equation 8. And here T2 from T1 is also a local diffeomorphism, which is given by the equation 7 and satisfies condition A1 and A3. And the finite one-sided limit of solutions of the system 8 corresponding to a local diffeomorphism we call the extreme point of the bisector. It is the point of the beginning of the bisector. And we proved a very important theorem, theorem 2. Let x0, y0 be the pseudo-vertex of the curve gamma in the boundary condition of the Dirichlet problem 1, 2. In this case, that finite left marker lambda is defined, and the coordinate functions of the pseudo-vertex satisfies these conditions of non-stationarity. Then equalities, these two equalities 11 and 12 are necessary, where k minus derivative and k plus derivatives are one-sided derivative limits of the curvature of the curve gamma at the pseudo-vertex x0, y0. And the solution of this equation 12 gives us the numerical meaning of left marker lambda. And under the condition of the theorem 2, the right marker mu of a pseudo-vertex satisfied this inequality for mu, which is another variant of the equation for the lambda when we change left and right borders of the limit. And we proved corollary 2 that under the conditions of this theorem, there are such two figures, alpha and beta, that alpha k plus derivative plus beta k minus derivative is equal to 0. And we have a remark.
You have 2 minutes, okay?
The remark that mu is equal to 1 divided by lambda. And then we consider an interesting example of a boundary value problem. So we describe gamma such a plot of two functions, gamma 1 and gamma 2, which depend on t. It's a formula which describes the curve gamma. And now we consider that this curvature has exactly 4 pseudo-vertices. The array of pseudo-vertices is equal to 0. Now you may see it. Then we calculated one-sided derivatives of the curvature, k minus and k plus in all these pseudo-vertex. For example, you may see its meanings in a point p divided by 4. And now you may see the plot of the curvature in a neighborhood of pseudo-vertex. You may see the propagation of the wavefronts. These red lines are singularity lines of wavefronts. And this is a case of the equation 12 for the left marker of the vertex. And the set of roots lambda you may see here. The only negative meanings of the lambda is equal minus 0.4028. And then we constructed a plot of the minimax solutions U from two variables x and y, which now is equal to the distance function from the point x, y to the set M. So we used our software complex, which is certificated in the state registration for the computer program. So thank you for your attention. Now I have finished.
Thank you. Only, do you have any questions, dear participants? Only one short questions because we have 1 minute. If no, I can ask only one question small. Is it significant that you use Euclidean metrics? Because always you specify this. Yeah.
Yes, of course, it is very significant because if they use not Euclidean metric, but for example, Manhattan metric.
Yes, yes.
So the structure of wavefronts may be very different, and they have non-smooth singularities, even if the set M is convex. For example, wavefronts from the point in Manhattan metric are equal to squares. So they have non-smooth angles, even if the point M is just a convex set.
Okay, thank you so much. Thank you.
You're welcome.
Again. Yes, so please, next speaker. Next speaker is Denis Kuzhutin, Nadezhda Smirnova, and Igor Tantlevsky, subgame Perfect Pareto Equilibrium for multi-criteria game with chance moves. Please, Nadezhda, you are the presenter.
Yes, hello. Yes. I would like to ask the previous speaker to...
yes, Pavel, please turn off your screen, sharing the screen.
Now I shall try to do it.
Yes.
Oh, I can't.
Maybe we can do it. We have the right to do it, Alina, or not? To stop sharing the screen.
Да, сейчас. Just a second. No, I stopped.
Great, thank you.
Yeah,
thank you.
okay.
Thank you.
I will try again then. Yes. Do you see my screen?
Yes, yes.
Yes, I will try to increase.
Yeah. Nadezhda, please follow the schedule. Yes, so you have 12 minutes for talk and some minutes for questions, okay?
Okay, thank you very much. So, dear colleagues, hello. My name is Nadezhda Smirnova, and today I present the work which was made joint with my colleagues Denis Kozyutin and Igor Tandlevsky. It's about multi-criteria game with chance moves, and our work concerns the existence of subgame perfect Pareto equilibria for such kind of games. Also, we want to find a way how to choose a unique optimal bundle of cooperative trajectories in this class of games. So, solving this problem, the following issues arise. You see it on the screen. So first of all, we needed to consider the single criterion multi-stage game with chance moves. Then we addressed to multi-criteria game with chance moves and prove that there always exists a subgame perfect Pareto equilibrium. And in the end, we show how to choose a unique optimal bundle of cooperative trajectories. So, but first of all, I recall the important papers. We work with them, and also the standard definition. Since we work with extensive game with chance moves, I just pay some attention to this resignation. It means the probability of transition from node X to node Y. And having it, we can calculate probability of realization of any trajectory which is generated by strategy profile U. And node by omega, the finite bundle of trajectories which is generated by profile U, strategy profile U. Then we can denote by this by Ash grade the expected value of player I, which corresponds to the strategy profile U, and having the pairs of players, which is vector. We can make the decomposition of extensive for game at any intermediate node. And we denote by UE with sample xt up xt the restriction of every player pure strategy for the game which starts at node xt. Okay, this slide is just for recall the definitions of subgame perfect Pareto equilibria, and the first one is for Pareto equilibrium, the second one for subgame perfect Pareto equilibria. I just noticed that this definition is a generalization for Nash equilibria. I mean that if we work with a single criterion game, this definition will define Nash equilibria in single criterion game and subgame perfect Nash equilibria here. So our goal is to show for any multi-stage game, multi-stage multi-criteria game with chance moves, there will exist sub-game perfect Pareto equilibrium. In order to solve this question, I need to say that it's well known that if we consider multi-stage, multi-criteria game without chance moves but with perfect information, it was proved that subgame perfect Pareto equilibria always exist for such kind of games in pure strategies. So we want to extend this result to multi-criteria games with chance moves. And first of all, we need to consider single criterion game with chance moves. The efficient algorithm to construct subgame perfect equilibrium here is a backward induction procedure. The problem is that it generates multiplayer subgame perfect equilibriums with different payoffs to players. So the first question we need to solve is how to choose a unique subgame perfect equilibrium and unique corresponding bundle of trajectories for this class of games for single criterion multi-stage games with chance moves. We will apply approach which is called attitude algorithm. In order to speak about it, we need to have for every player attitude vectors, which show how each player can influence on the payoffs of other players if he's in situation when he's neutral to his own payoff. I mean that if we have a situation that Fig equal to 2, it means that player I will try to maximize the payoff of player 2 in first order if he's in situation when he compare the payoffs where he has the equal result for himself. We will see later the example of implementation of this method. So the attitude subgame perfect equilibrium algorithm tells that if we are in situation that there are multiple nodes where player E is indifferent to the choice, he will try to affect the other player's payoff. So he will try to maximize at first the payoff G. If we again have a situation that the player for player E, for player G, we are indifferent to the choice of nodes, we look at the player L, which is on the third place for the player I, and continue in this way. As the result, it was proved that using this algorithm, we will construct a unique subgame perfect equilibrium in pure strategy for any extensive for game with chance moves. Let's look at the example here. I will skip. Yes, I will skip an example because the time is close to finish. Here we are in the situation where player 2 is he may choose this node or this situation or this node, and we see it because he has some preferences on the third player, he will choose that result. So let's continue to the multi-criteria extensive form game with chance moves. There are more than one criterion. It is always possible to make a correspondence with a single criterion weighted game in by Formula 2. And since for the single criterion game we have attitude algorithm which for which we always have a subgame perfect equilibrium, it means we always can construct the subgame perfect Pareto equilibrium for the initial game, multi-criteria game. So the following question arises: how to choose these coefficients lambda? And here we apply the idea of approach which is called minimal sum of relative deviations. Here every player tried to minimize sum of deviations from the best point for himself, and it was shown that that every player should use the coefficients in this form. Here H star is the best result for the player for criteria K, and this one is the worst result for the player. So using these coefficients, we can construct the single criterion game. For this game, we can apply attitude algorithm and construct subgame perfect equilibria. As the result of our paper, we proved that the existence of pure strategy Pareto equilibrium for arbitrary and Pearson extensive for multi-criteria game with chance moves, and introduced the refinement which is called mu subgame Pareto, subgame perfect Pareto equilibrium, which allows to construct a unique subgame equilibrium. So thank you for your attention. If you have any questions.
Dear participants, do you have any questions?
Elena, I have.
Yes.
Can you hear me?
Yes.
I have
we
a
hear.
Short and very basic question. When you talk about Pareto equilibrium, Pareto refers to what? To the way you are aggregating the different criteria, or it means that what you are getting is an equilibrium that is Pareto, because the terminology here can be a little bit confusing.
Nadezhda, if you show us the first slide, because the definition of Pareto equilibrium is very different to the classical one. So you assume like Nash equilibria, but you call it Pareto equilibrium.
No, I mean the Pareto equilibrium, which is it's given by this definition. For if we work with one criteria, it is called the Nash equilibria for single criterion game. Maybe I don't understand the question.
No, I'm probably I am guessing what is going on here, because you are using Pareto concept in order to transform your game, which is multi-criteria game, into a single game.
Yes.
So the way you are aggregating the different criteria is Pareto. But the equilibrium itself is not Pareto optimal.
Yes.
Anyway,
I understand in the same way.
I may be completely confused here, but it will help if you make it a bit more precise. I mean, in the paper.
And the definition. So okay.
And I have one small question. So if I understand well, so do you have, like if you have many Pareto equilibria, you want to find one, and you have a preference on other players for each player. So every player has a preferences, and after that, so you have a unique Pareto equilibrium using these preferences. So you add, it's like additional characteristics of the game, and you find the unique.
Yes.
Okay, I understand. Yeah. Okay, but when you find this like Pareto equilibria, you have like a linear combination of criteria or not? So you find Pareto like having all criteria in a vector form?
Yes, when we find a Pareto equilibrium, we use coefficients and scalarized game.
And strictly speaking, we try to find some appropriate coefficients. We call them mu. And to consider some scalarized game. And let me just return to the Pareto equilibria definition. Please show the slide.
Yeah.
This is the classic, here in left-hand side and right-hand side, we have a vector. And this vector inequality means that by each criterion, the left-hand side is greater or equal than right-hand side, and at least one inequality is strict. So this is a classical definition suggested by Shapley. So this is just vector inequality. So sorry for confusing.
Okay, now it's clearer. Yeah.
Yes. Sorry. Because when you have great or equal, it means it is confusing that you have one of strict. Okay. Okay. Thank you for the presentation. So we have a break until 4:30. Yes. And after that, we will meet. I will be here. Surya, are you here? Surya, nice to see you.
Nice to see you too.
You will be the first speaker. Yes, not Victor.
I know. Yes,
not Victor.
Yes,
Okay,
yes,
okay.
I will.
Echelon supply chain.
Yes.
Very new topic from your.
For me.
Yes.
I'm studying the terms of this area of knowledge. And a lot of different applications of mathematical areas, different mathematical areas. But I'm feeling as a new in this area of knowledge. I will try.
Okay, okay. Victor is not coming, as I understand.
He was going, but I don't know.
So maybe he's coming right now. Yeah.
Maybe.
Okay, okay.
I have talked to him yesterday, no, the day before yesterday, and he was going to join us because here is our report, our presentation, and Alexander Mugayskih presentation. That's why he was going, but I don't know whether he is here or not. I don't see him here.
Yes, yes, yes.
We will wait.
1 minute. I think you can start sharing screen. Yes, because we have very, very limited time. So you
I have
please be very, very brief in your presentation.
Okay, I will try. Is there my
yes, we see.
In the screen. Okay, shall I start?
No, I will present you. Yeah.
Okay, excuse me.
Of course. So I need to present you. You borrow my work. So we start the last session for today in a section game theory, conflict system control. It is part 3, and we have 3 presentations. And the first one, it is made by Surya Kumachova, joint work with Viktor Zakharov, 2 echelon supply chain, market search, behavior and dependent demands. So please, I think we can start. Yes. 12 minutes. Yes, and
okay. Okay, I will try. I will do my best. Okay, thank you very much, Elena. My co-author Viktor Zakharov and me would like to present you the results of our study, which is called 2 echelon supply chain, market search behavior, independent demands. During our presentation, we will review the related models devoted to the problems of 2 echelon supply chain. We will formulate our model and search for the equilibrium conditions. And after it, we can discuss the main results of our study and further prospects of it. Well, nowadays supply chain management is one of the most popular and intensively developed areas of applied mathematics. The necessity of studying and modeling the processes of interaction between the manufacturer, suppliers, and final purchasers of products requires such mathematical tools as game theory and applied statistics. One of the first papers devoted to this problem was published in 1988 by the author Parlar. And after it, we can see the development of supply chain management, of mathematical applications to these problems in further works, especially in such latest works as presented here by Kerbach and Mock and Kumara and Sharma and co-authors. This is the models of last years, I can say. Along with these models, we are consider the
papers devoted to optimizing the supply chain of one specific product by Yukin and co-authors, published in 2015. They consider two echelon chain, which includes one product manufacturer and two retailers. In the current paper, we studied the issue of optimizing the supply chain of one specific product also. To illustrate this problem, we consider an example of two echelon chain, which includes one product manufacturer and two retailers. We can say that our model is similar to the mentioned one, to the last model presented in this slide. But in the mentioned paper, both retailers' demands were assumed to be random and independent of each other. But we suppose that in general case, such an assumption is incorrect and may lead to false conclusions. On the contrary, we suppose that the real practice may design various types of dependence between these variables. Thus, in our paper, we consider their joint distribution as a given function and try to apply our hypothetical knowledge about the distribution of a given function to the game theoretical model formulated by Yukin and co-authors. To formulate our model, we consider two echelon supply chain model, which consists of one manufacturer and two retailers, which are the purchasers of one product produced by manufacturer. Let C be the unit production cost, omega is the wholesale price, and P is the market price of the product, which is supposed to be fixed for both retailers. We consider delta I and delta G as a retailer's demand. As I have said before, we suppose the main assumption of our model is in that delta I and delta G are continuous variables which have joint cumulative distribution function of capital and the representation of joint probability density function naturally, yes, f small. In the case when the local demand of the first retailer exceeds its order quantity Qi, the unsatisfied demand of this retailer goes to the second retailer with a probability beta I, and the retailer I loses sales, which unit cost is Bi. If the retailer, the second retailer, also doesn't have enough order quantity to satisfy demand switched from the retailer I, then the manufacturer loses Bm, which is the cost of brand loyalty. The studied model can be considered as a hierarchical game with rational players. Each player's aim naturally is to maximize her own expected profit. It means that her aim is to choose positive value of order quantity. Being the high-level player of this hierarchy, the manufacturer chooses the strategy. It means that she determines the wholesale price omega of the production. The retailers need to choose the other quantities under fixed omega. We can consider their interaction between manufacturer and retailers as a Stackelberg game in which the manufacturer is the leader of the game. That's why we can consider the behavior of the retailers as the best response on the leader's strategy. At the same time, we can consider the interaction between retailers as Cournot game and search for Nash equilibrium in this game. In general, we can say that the strategy profile of each strategy profile for the system, yes, is the system of variables, omega, Qi, and Qj. But in the current study, we consider the manufacturer's control tool as a wholesale price, omega, to be fixed. That's why the retailer's control tools can be considered as Qi and Qj, respectively. The players' profits are the functions of their own strategies in this case. we can obtain the manufacturer's total expected profit in the form 1, as the expression 1, where the first summand is the profit that manufacturer receives from the sales, and the second summand is expected loss of brand loyalty cost, as it was discussed before. Then the expected profit of retailers can be obtained in the form of the expression 2. The total demand of retailer consists of the local demand and the demand switch from the other retailer when there is no enough stock. To obtain the equilibrium conditions, we need to analyze the retailer's expected profit. For this purpose, we need to analyze each summand in this function and to consider 2 cases to express the minimum value of this expression. Analyzing this by 2 cases, considering of 2 cases, we obtain finally then expected value of this minimum can be expressed in the form of the equation 3. Excuse me. To analyze this probability, we can apply our knowledge about probability theory and obtain the results using the properties of joint probability, which is supposed to be known in our case. To obtain the structure of this probability, we formulate auxiliary lemma, which is in that the probability of this double inequality depends only on the joint distribution of both demands J, delta I and delta J, and the values of the other order quantities, Qi and Qj, in the following form, in the form of the expression 4. To prove this lemma, we denote the right side of this inequality as phi capital. Further, we consider 2 double inequations and obtain their union and obtain the probability of their union, applying the properties of arithmetical properties of probability. Applying our hypothetical knowledge about cumulative distribution function, the function of the joint distribution, we obtain all the summands of the mentioned expression. And using them, we obtain the lemma as is in form 4, the expression 4. The lemma can be considered as proved. And after it, we need to analyze the summands of the expected profit of each retailer. Once again, using the properties of joint distribution, we obtain the expected values of each summand, applying our knowledge about joint distribution. And when we suppose that this joint distribution is known, we can obtain the first summand of the retailer our expected profit. And using the similar way of reasoning, we can obtain the second summand using our knowledge about the joint distribution. From this equation, from the equation 4 and 7, we can obtain that the first derivative of the retailer our expected profit and obtain the extremum conditions in the form 8, where function phi was defined in the conditions of the lemma. Similar for the expected profit of the retailer J, we can obtain the extremum conditions in the form 9, defining psi by a similar way in the form 10. Now we can formulate obtained theorem, which is in that non-negative solution of the system 8, 9, forms Nash equilibrium in 2-echelon supply chain model with market surge behavior and dependent demands of customers. If we want to formulate an equilibrium conditions and expected profit for manufacturer, we can define it from the equation 1 for any solution of the system 8 and 9, which can be obtained in general terms of the joint distribution, which is hypothetically known function. As the main results of our study, we can say that the model of two-echelon supply chain with market search behavior independent demands of customers was formulated. The specific feature of our model is in that the retailer's demand during distribution is supposed to be known. We proved auxiliary lemma and obtained the equilibrium conditions for this model using the properties of known joint distribution. As further prospects for development of our model, we see clarifying the form of the joint distribution function, and then we will obtain particular cases of the application of this model and can analyze model in each particular case. Here are the references which we used in our study are represented. And now I would like to thank you very much for your attention and answer your questions.
Thank you. Dear participants, do you have any questions about the model? I have one question, maybe several questions, I don't know. So for you, you assume that the first level, so the manufacturer is not a player. Yes, so
yes,
W is fixed.
We are accepting this player because his strategy is fixed, is supposed to be fixed in this game, because it is only the previous step of our study, the pre-study, if we can say.
Okay.
And in the framework of this step, we are considering only interaction between two retailers. And after it, we can apply the results of the theorem, results of the equilibrium conditions. We can use them to analyze the manufacturer expected payoff and include him in this game also.
Okay. Any questions?
Maybe I have one small comment. Yeah. Better not to use here Cournot model or Cournot equilibrium, because in Cournot the price depends on the total quantities, and here there is no such dependence. So just to avoid any misunderstanding with economists, better to say that you are computing a Nash equilibrium, a simultaneous game. You don't need to refer to Cournot. And of course, it would be really interesting when you introduce the manufacturer as a leader, because now the ordered quantities can be eventually managed better by the decision made on the wholesale price. And now eventually you can study also one case where the manufacturer is obliged to have the same wholesale price for the two retailers, and the case where it can eventually discriminate between the two and having two different wholesale prices. This would be really interesting.
Okay, thank you very much. We will include this feature in our consideration, and I think it will improve our model. Thank you.
Thank you. I think we can stop here. And the next speaker. Thank you for
thank
the
you very
presentation.
much.
Yes. And the next speaker is myself, and I will share the screen. Surya, can you stop sharing the screen? And
okay, excuse me.
No problem. I will try to do it.
I have stopped.
Yes. It's,
okay.
I'm not so fast.
We all are not so fast.
Okay. So I'm presenting the joint work with Vladimir Buren, Ksenia Starovera. We are all from St. Petersburg State University, and the topic is data modeling with cluster analysis. So the plan, I will be very fast, and the plan of my talk is the following. So at first I will present, maybe you do not know, what is data modeling with two factors. And after that, so the result of this data modeling, it is the formulation or forming the data set for clusterization problem. Then we apply the new method of clusterization borrowed from game theoretical problem. And after that, I will introduce our results on numerical simulations. So first, some words about their modeling. So their modeling is needed to, it may be with different factors, and it is needed to to estimate the efficiency of firms. So here we assume that we have the finite number of firms and they produce homogeneous product and provide similar services. And we refer to the Copen-Douglas productivity function. It is function 1, when we estimate productivity, total production, as this multiplication. So K is a capital input, L is labor input, alpha, so alpha and beta constant represented the output elasticity of capital and labor, respectively, and A is a constant represented the total factor productivity. So we assume that for any firm, we have these 3 numbers. So we have Y production, total production, we have K capital and labor numbers. And we not only have one number, but we observe each firm during some finite interval in discrete time. And our problem is to estimate the efficiency of the firm at some time interval, order the firms, so find something like the series, yeah, and after that apply their modeling to find the estimation of the efficiency of every firm, and find the partition of firms into the subset of firms with close efficiencies. So the idea is like, if you have money, for example, for distributing among researchers, you want to have some classes, like in cluster analysis, you want to have some classes of firms with close efficiencies. And you can do this using this cluster analysis and applying, so giving some money to each cluster. And this is the main formula, the main characteristic of a firm's efficiency. It is formula 2. So it is the ratio between production and linear combination of capital and labor input with coefficients delta. And in this DAM modeling, we want to maximize the efficiency of firms. So we will solve the optimization problem on the set of admissible values of coefficients delta. So this is capital D is the set of possible values for these parameters. So all delta are positive or non-negative, and the efficiency is limited by 1. So with what is the steps of their modeling? First step is to solve the N optimization problems. For each firm, we formulate the problem of maximization these coefficients over the set of possible delta given from set D. And we solve this. It is proved that in their modeling the solution exists. It is a linear problem. So we solve this and find the efficient of each firm. Yes, the coefficient of efficiency of each firm. And the maximal one, the maximal value of this coefficient is 1. After that, we can formulate the series, so the ranking, the ordering system of these firms, and some of the first firms are with efficiency 1. It is the most efficient firms, and we have this ordering for all the set of identical firms, and we prove the theorem in which we formalize the equivalent problem. So if we consider the inverse problem, so inverse coefficients, so it is 1 divided by t, so we may consider inverse efficiency coefficient as I, and do the same but for this inverse coefficients. In this case, we solve an optimization problem of minimization problem, but the set of the parameters at set 1, set 2. So we minimize it over the set of these possible parameters. They are again non-negative, and the inverse efficiency is greater or equal than 1. Now we solving this minimization problem 7, we get the solution, and we again can order the firms like in non-increasing way, yes, of efficiency. So here we have the most efficient firm with lowest inverse coefficient of efficiency. And this is the theorem which proves that these two problems are equivalent and some properties of this solution, optimal solutions. Now we have this, so we solve this optimization problem for any firm and for any time period t, which is from 1 to capital T. For example, we solve it for inverse efficiency coefficient. And after that, we form the time series for each firm. The next problem is to clusterize the firms into some subsets. And now we have not like points, but we have time series. And we want to apply the clusterization problem to time series. So, and this time series with some properties, because they have something like the ideal point. So the ideal point is 1. When it is 1, it is the most efficient firm. So the next step is to apply clusterization procedure to this set of firms. To find the partition of firms, we can apply like regular clusterization methods like k-means, for example, yeah? But we have specific material time series, and we want to provide new procedure based on game theoretical model, because I'm in this section. So here, the idea is to transform the problem of clusterization to the game theoretical problem. And if you consider clusters, it means that you find the set of disjoint subsets, yes? And this is very close to finding the coalition structure stable in some sense. So we will do this procedure, yes, using clusterization procedure, using the idea of finding stable coalition structure. And to do this, we need to define the characteristic function to define the cooperative game. And we defined it in a special way. So the first step is to find the measure of correlation between time series. So we have one series characterizing one firm Si, and another Sj for the second series, for the second time series. This is we borrowed from this paper. So this is the correlation measure between two time series. And after that, based on this measure, we can define the distance between time series using this formula. And we also need to have similarity for constructing cooperative game. And we define similarity as 1 minus distance, yes, between two objects, time series. And characteristic function is defined in this paper. And we defined it in this way. So we calculate the distance between the similarity between the objects inside cluster. So the more the similarity, the more the value of characteristic function. And here you see the distance between the object inside coalition and outside coalition. So the more the distance between the objects outside and inside, the more the value of characteristic function. So it is in some sense and a good idea how to define the characteristic function for this special class of problems. And based on this function, so we construct it, and it may be not super additive, of course. And we, after that, we transform, so we may consider the game with coalition structure. And we apply the idea here to find one or maybe several coalition structures which are stable. And here we use the idea of stability, which was proposed in the joint work with Artyom Sidakov and others. And we use for this the idea of stability like Nash stability. It means that no firm can benefit from deviation from a current coalition structure. So if it deviates, he will lose some payoff, yes, meaning taking into account that payoff in all coalitions are calculated in the same way. So here we can use different approaches how to calculate the payoff of the firms, and here we apply Aumann-Dresser value and equals plus solution here and redistribute V of Q among the firms in this coalition. And what we have here, so what about the existence results? So existence is proved in the paper of Gusev and Mazalov in 2019. They proved the existence with respect to the Aumann-Dresser value. So we always have stable coalition structure or stable result of clusterization, but it may be not unique. So, but for about the second one, the equals plus solution, it is not proved the existence, and we have the examples in game theory with when it doesn't exist. But here in our experiments, we always have existence, but not uniqueness as well. And here is the result of numerical simulation. I will briefly explain you what we have. So in our numerical simulation, sorry for our Russian because pictures were made. So this is bakeries. It is only 10 firms. We have 10 firms, and we observe 3 parameters: Y, K. I have minutes now. We have Y, K, and L. Yes, so 3 parameters, and this is different colors refer to different firms. Yeah, solving optimization problem for each time period, we find the coefficient of efficiency, but this is the inverse coefficient of efficiency of these firms. So you see here that the closer to 1, the most efficient firm we have. Yes, so this firm, orange firm, is not efficient, especially at the end of time period. Yes, T, capital T. And as a result, we apply our method and we find the unique clusters for the unique partition of the objects of firms. And with respect to both equals plus solution, Aumann-Dresser value. And this is, you see here, the cluster contains, yes, this is the first cluster, contains only firm 1. It is the lowest efficiency firm. Yeah. The second cluster is the cluster with middle efficiency, 2, 4, and 8. And this is the last cluster with most efficient firms. So you see here, this coefficient is much closer to 1 than others. So this is the method how can you cluster to find clusters or sets of the firms close in efficiency using game theoretical methods. Thank you, I'm done. If you have any questions, you are welcome.
Thank you for your presentation.
May I ask a question, Elena?
Yes.
I mean, here you are using game theory as an algorithm, because
yes,
these companies are not really cooperating or whatever.
Yes, of course.
Now you are obtaining this result that you have a partition with 3 subsets. Now I'm wondering what would happen if you computed simply the average efficiency of all these firms. What would you get in terms of efficiency?
In reality,
in terms of clusters. No, you're using the same data set, because the procedure you are using, I mean, it has some algorithmic interest for sure, but typically when we do cluster analysis, we have a huge data set, and for this reason we don't know a priori how many clusters we have, and we need to do it. But here, if you have a small number of firms, actually it can be done in many different ways. And if you want to show that your algorithm is better than others, maybe you have to compare the results with what you would have obtained with
it's a good suggestion. Yeah, because we even didn't compare with k-means, but maybe yes, the result will be the same.
It can be with k-means, can be with Ward, with any algorithm that is widely available.
Thank you so much. Thank you. Any other questions? We have no time for questions. So thank you. And the next presentation, I will stop sharing. how to do it. Okay. And the next speaker, please share the screen. It is Alexander Mugayskih, and the topic is cooperation and vehicle routing game on a megapolis network. We cannot listen to you.
Actually, we can see you.
Alexander, we can see you, but we cannot listen to you.
His micro is muted, I guess.
Yes, yes. Okay, now it is okay.
Hello, do you hear me?
Yes, yes.
Hello, my name is Alexander Mugayskih. I am from St. Petersburg State University, and my report will be about cooperation in vehicle routing game on Megapolis network.
Alexander, please, you have this part, we see not only a screen, but also the part of, yeah, it's better now.
Now some words about my research outline. Firstly, I will speak about current problems on vehicle routing on time-dependent network and about cooperation in VRP. Then time-dependent vehicle routing problem and the joint statement of the problems TAP and VRP will be formulated. The main aspect of my work will be about static cooperative routing game on time-dependent network, and I will present direct coalition induction algorithm. Also, an example of static cooperative routing game on time-dependent network will be presented in my report. Constantly increasing level of traffic congestion is becoming an essential reason of economic losses. Most of the models nowadays assume that the travel speeds are constant and they ignore the fact that travel speeds can change throughout the day. In practice, this solution becomes non-optimal and non-feasible in some cases. As a result, time-dependent approaches consider traffic information, and that helps users to avoid well-predictable traffic congestion in offline vehicle routing. Now some words about cooperation in VRP. Horizontal cooperation between freight forwarding companies aimed to deliver any kind of goods for customers can significantly decrease operational costs for all companies involved. The main idea of cooperation in routing problems is that companies can form coalitions and redistribute customers. The major part of existing studies on cooperative logistics is devoted to possible strategies of transport collaboration and cost allocation. But usually only two types of cooperation are usually discussed. This is order sharing and capacity sharing, but no details in solving routing problems are provided. As a result, due to the heuristic nature of methods applied for solving routing problems, the main property of cooperative game theory, sub-additivity of characteristic function, can be violated. This leads to unstable cooperation and unfeasible cost allocation in some cases. Now, on this slide, you can see time-dependent multi-depot vehicle routing problem formulation. I will probably miss it. The target function is denoted by Formula 1, subject to constraints from 2 to 5. The travel time function is usually applied in time-dependent models, and you can see it on this slide. Travel time function states for the travel time that the road on H from I to J will last when the user starts his journey at the moment BI. On this picture, you can see 3 periods of the day. Probably there is a morning rush hour and the evening rush hour when the time is bigger than, for example, in the afternoon. There are special traffic information systems in European countries that collect information about traffic and on the road network, for example, in Germany, in Italy, and the United Kingdom. For example, in Berlin, information on every edge of road network is collected for 200 5-minute intervals. And then such services provide information for logistic and freight forwarding companies to solve their problems. In my previous works, I presented the joint statement of traffic assignment problem and vehicle routing problem. I will shortly discuss it. St. Petersburg road network was presented as a graph. Then correspondence matrices were estimated by experts of St. Petersburg State University, and traffic assignment problem was solved by Franken-Wolf algorithm for every period of the day, and user equilibrium distribution was found. As a result, we get travel time matrices for each period of the day, and travel time function was set for each graph, for each arc of the graph. In this slide, you can see St. Petersburg road network. The main part of my report is about static cooperative routing game. There is a set of companies engaged in transportation service. Each company provides transportation service to a given set of customers. The total cost of collision is denoted by formula 7. It consists of two parts. The first part corresponds to rent for vehicles, and the second part corresponds to the total duration of all routes used by this coalition. We will construct the characteristic function of cooperative routing game which will satisfy the sub-additive property. Firstly, we consider the following cost minimization problem on the set of feasible routes. You can see this problem by formula 8. We denote by C-opt the exact minimum value in the problem H, and by CH the solution of this problem obtained by a heuristic algorithm. Due to the heuristic nature of algorithm, because they do not always generate optimal solutions, the inequality 9 is true. Then we take two intersecting coalitions, C and A, and for any feasible routing plans PS and PT, the routing plan representing the union of PS and PT is feasible in the routing problem for joint coalition of S and T. So we have such inequality. With the help of 9, we obtain this inequality, and then we consider coalition L and coalition S minus L. So it follows from inequalities 9 and 10 that the optimal solution less than these two parts. So we can form the direct collision induction algorithm and by defining the value of characteristic function in cooperative vehicle routing game in the following way, formula 12. This characteristic function defined by 12 of static cooperative game will satisfy sub-additivity condition. It follows from constructing of this characteristic function. Now some words about experiment. There were 3 freight forwarding companies from 40 to 70 customers. 2 types of ERP formulations were considered. Time-dependent horizon was divided into 5 parts, and characteristic function values were calculated according to the direct collision induction algorithm. So the algorithm was used genetic heuristics. The results you can see on this slide. You can see that for delay flow solution, characteristic function value practically for all coalitions is less than for free flow solutions, and the percent of improvement you can see in the last column. The difference between roads you can see on this picture. Free flow solution and delay flow solutions, the difference is about 10 minutes. Shapley value was used as a solution of this vehicle routing game. For example, for coalition S1, cost before comparison were about 690, and cost based on Shapley value was about 437. Cost reduction coefficient, you can see, is about 24, from 24 to 37%. And there is the difference between how customers were redistributed without cooperation and with cooperation. Customers are squares, triangles, and circles. So results. In this work, special class of VRP was considered. It was cooperative routing game on time-dependent network. A direct collision induction algorithm was proposed. It guarantees the sub-additive property of characteristic function in this game. Freight forwarding companies are able to save about 30% of costs by forming coalitions on time-dependent network. And an example of static cooperative routing game on St. Petersburg time-dependent network was presented. Thank you for your attention.
Thank you. Any questions? I have a question about your experiment. Is it really so applied that you have two types? Is it the solution that you have? But can you show, Alexander, we also have this screen.
Okay.
Yeah. So you have two types of solution, FF route and DF. So with delays and without delays, yes?
Yes.
So if you take into account delays, we will have less time, of course, route. Yeah, but this is calculated only for experiment, but or it is involved in some systems, in real systems now.
It wasn't involved in any systems, but the travel time matrix was real. So this route and these durations are practically.
So you have in the right picture, right-hand picture, you have more routes or not? So you have different routes, yes, here.
Yes, free flow solution and delay flow solution generates different routes. For example, free flow solutions uses the starting point is this, and so it constructs the route through Petergovskое шоссе, and probably this leads to bigger duration time.
But this route is on the sea, no? So you have the route partially on the sea. Yes, here no, it is the route on the roads or not. So this is only it is not the roads. No?
It is not the roads. Why?
Yeah, I mean, in the left-hand side, you have only a straight line, but we have like.
So my graph was contains 255 nodes. So I can't create the graph that considers practically all intersections of all roads. I take nodes only at intersections of main highways and roads. So the points are.
Okay, I see.
So I can't create a very big graph, only 255 points.
Okay. Dear participants, do you have any questions? If no, we say thank you for the speaker and we finalize the work of our session. Thank you so much for all participants and see you the next time.
Thank you very much.
Thank you so much. Goodbye.
Goodbye
to everyone. Goodbye.